Welcome to another session of our reading group on the assumptions of physics. Today we're going to continue reading and talking about the experimental verifiability and how from experimental verifiability we get a logic that then at some point will lead to topologies and sigma algebras. So I'll put, as usual, the link in the chat for people who want to follow. And I should share the text. And there are a lot of people that couldn't join today, so it's just the three of us. Let's see if the sharing is working. Yes, so Ben, you can start.
Yeah, so should I start with the corollary or?
No, I think here.
Okay. All right. We introduce decidable statements here because their definition and related properties clarify what happens during negation, but they do not play a major role in our framework. They represent a special case which we will turn to time and time again over the course of the work. Combining verifiable statements with conjunction, i.e. the logical and, is more straightforward. If we are able to verify that the animal is a swan and that that animal is black, we can verify that that animal is a black swan by verifying both. If the tests for both are successful, then the test for the conjunction is successful. That is, if we have two or more verifiable statements, we can always construct an experimental test for the logical and by running all tests one at a time and check if they're successful. Yet, the number of tests needs to be finite or we would never terminate, so we are limited to the conjunction of a finite number of verifiable statements.
All right. So axiom of finite conjunction verifiability. The conjunction of a finite collection of verifiable statements is a verifiable statement. Formally, and is this a sequence now?
Yes.
Yes.
It's a finite sequence.
Let sequence in SV be a finite collection of verifiable statements. Then the conjunction of all these SIs is an element of SV is a verifiable statement. Justification. Let the sequence of verifiable statements be a finite collection of verifiable statements. Then we can find the corresponding set of experimental tests, again, being a sequence in experimental space.
Yeah, the set of experimental, experimental tests.
Such that the result of EI and A is a success if and only if A of SI is true for all A in A of S. Let the conjunction of experimental tests be the procedure defined as follows. 1. For each I from 1 to n, run the test EI. 2. If all tests terminate successfully, then terminate successfully. 3. Terminate unsuccessfully. The experimental procedure so defined is repeatable, can be executed by anybody. Therefore, the conjunction of all experimental tests is an element of experimental space. We have for every A of in AS, okay, how to, sorry. We
the
have
result
that
of the conjunction.
Yeah, for every A in AS, the result of conjunction of experiments and A is a success, if and only if the result of experiment I and A is success for all I's, if and only if A of SI is true for all I, if and only if A of the conjunction of all SI's equals true. Therefore, the conjunction of all verifiable statements is a verifiable statement. We are therefore justified to assume that the finite conjunction of verifiable statements is a verifiable statement. Note that this cannot be generalized to infinite collections, as the procedure would not be guaranteed to terminate. In fact, if the only way to test the infinite conjunction is to teach to test each statement individually, then we are guaranteed to take infinite time and the test will never terminate. Therefore, we are not justified to assume that the infinite conjunction of verifiable statements is verifiable. Just to understand, so when we are looking at this result, so the result is always a function of two variables. So we have first the experimental test, and A is the what is it? Is a value, a truth value of the statement, or
It's
how
the
to?
possible assignment. So it would be the case in which A is equal to truth.
Okay, okay. Sorry, and this, let's say this result function, have we discussed? We have discussed before, but can you just briefly remind, like, what is this possible values? Like, if we
Success, failure, and undefined. There you go. Success, failure, undefined.
Okay, so then this small a denotes this truth assignments of all these. Like, okay, and then EA is experiment. I see. Okay.
Yeah.
Thanks.
And we are here. There you
All right. Combining verifiable statements with disjunction, i.e. the logical OR, is also straightforward. To verify the swan is black or white, we can first test that the swan is black. If that's verified, that's enough. The swan is black or white. If not, we test that the swan is white. That is, if we have two or more verifiable statements, we can always construct an experimental test for the logical OR by running all tests and stopping at the first one that is successful. I can see where the topology is going to happen. Yeah, because we stop at the first success, the number of tests can be countably infinite. As long as one test succeeds, which will always be the case when the overall test succeeds, it does not matter how many elements we are not going to verify later. But it cannot be more than countably infinite, since the only way we have to find if one experimental test in the set is successful is by testing all of them one by one. Therefore, we are limited to the disjunction of a countable number of verifiable statements. All right. Sorry, I keep giving you the long axiom statements. We can break it up into two if you want, but
yeah, let's see how it goes. Okay, so axiom of countable disjunction verifiability. The disjunction of a countable collection of verifiable statements is a verifiable statement. Formally, let the sequence of in SV be a countable collection of verifiable statements. Then the disjunction of these SIs is a verifiable statement. Justification. Let the okay, so now we have infinite sequence in SV be a countable collection of verifiable statements. Then we can find a corresponding set of experimental tests in E such that the result of experimental tests and truth assignments is a success if and only if A of SI is true for all possible assignments. In this case, we have to be careful to handle tests that may not terminate. Let the infinite disjunction of experimental tests be defined as follows. First, initialize n to 1. 2. For each I from 1 to n, run the test EI for n seconds. B. If EI terminates successfully, then terminates successfully. 3. Increment n and go to step 2. The experimental procedure so defined is repeatable, can be executed by anybody. Therefore, the infinite conjunction is a part of experimental space. The procedure will eventually run all tests for an arbitrarily long amount of time. Therefore, for every truth assignment, the result of infinite disjunction of experimental tests and some value truth assignment is a success if and only if the result of one experimental test and the truth assignment is a success for some I, if and only if the truth assignment of Si is true for some I, if and only if the truth assignment for infinite disjunction of statements is true. Therefore, the infinite disjunction of statements is a verifiable statement. We are therefore justified to assume that the countable disjunction of verifiable statements is a verifiable statement. Note that this cannot be generalized to uncountable infinite collections, as the procedure would not be guaranteed to eventually run all tests. In fact, suppose the only way to test the uncountable disjunction is to test each statement individually. We would then need to at least run all of them for a finite time, say 1 minute. Even assuming arbitrary long time, we would only have countably many minutes at our disposal. Since the set of tests is uncountable, we are not going to be able to run each test for 1 minute. Therefore, we are not justified to assume the uncountable disjunction of verifiable statements is verifiable.
Yeah, there is actually a better way to say this now that I know more math. If you have a collection and you're trying to make make an assignment, you have an infinite collection and you want to make an assignment to each element of a real number such that the sum of all the real numbers converge, then they can be non-zero only on countably many. So this is a resulting set theory. So basically you say, okay, I have these tests, I have to run them, I assign some type of amount of time to each of them. I can only run actually countably many. So that's basically what this is saying.
So I did want to make a not very relevant comment, but about the experimental setup itself.
Yeah.
These types of things come up. I'm sure you've seen them before, but they come up sometimes in complexity theory. And the experiment that you've written down, it goes through all the like it does the thing that you want it to do, but it can be much less efficient, like in terms of big O time. There's a way of getting the same I guess like up to a polynomial the same runtime for this experiment as for just doing like one of the experiments. And that's by instead of incrementing n by one, you double it each time. So each time you're running twice as many tests and you're running them for twice as long. And then you can work out just because all of the previous runs are so much they do so much less computation than the one you're doing right now. The whichever one happens to succeed is going to have like is going to be most of the runtime, and so it's like big O of however long it took to just run the correct experiment for the first time. It's not necessarily more efficient, but at least from a complexity theory standpoint, it's like equivalent, which I think it's a funny way of doing it.
Yeah, yeah. So we're not essentially here we're assuming that the only resource that we have is time,
Yeah.
and we are not even being efficient about it because it's just proof of existence. I have no idea whether putting the resource manager of time actually would give you some space that is would be interesting for physics. I have no idea, and part of it is the usual. Sort of circular reference. Well, how do you define time? Well, I define it with, some reference in experiments, but then how do you define the time that you use for it? There is the sort of recursiveness of things. So I don't know. So I'm like I say, I'm really not looking at all of those things, even though I have studied complexity theory like 20 years ago, and so some of these things are in the back of my head.
Yeah, okay, yeah. I know it's not, yeah. It doesn't actually have anything to do with the point of this, which is that you can do this experiment, which is very cool. All right,
Yeah,
yes.
no, but it sort of leads. I mean, like as I said, like my background, comes more from engineering, and I did, software engineering. So I studied a lot of similar things, and somehow they stayed in the back of my brain, and they're sort of reconnecting, and so yeah.
Yeah, okay. Yes, let's yeah, proposition 1.33 or 1.33. The conjunction and disjunction of a finite collection of decidable statements are decidable. Formally, let some sequence Si from 1 to n be a finite collection of decidable statements. Then their conjunction in and the disjunction are decidable statements. Yeah, okay. Yeah, their conjunction and their disjunction are both decidable statements.
Yeah.
So proof, let this sequence Si be a finite collection of decidable statements. Then then this sequence is a finite collection of verifiable statements, and their negations are also all verifiable. So consider the conjunction of these statements. This is the finite conjunction of verifiable statement, and therefore is a verifiable statement by 1.31. Then we consider its negation, so not then the conjunction of all of them, which is the same as the disjunction of the negations of all of the statements. Then this is the finite disjunction of verifiable statements, and is therefore a verifiable statement by 1.32. The finite conjunction of decidable statements is decidable by definition. Similarly, consider the disjunction of all of the SIs. This is a finite disjunction of verifiable statements and is therefore verifiable by 1.32. And if we consider its negation, which is equivalent to the conjunction of the negation of all of the statements, then this is the finite conjunction of verifiable statements and is therefore a verifiable statement by 1.31. The finite disjunction of decidable statements is decidable by definition. Note that this cannot be generalized to infinite collections as it would require closure under infinite conjunction. Also note that this result is consistent with the experimental tests given by 1.31 and 1.32.
Taken as a whole, finite conjunction and countable disjunction define the algebra of verifiable statements. It is limited compared to the algebra of statements, and it tells us that in practice, we are not going to be able, in general, to construct an experimental test whose success is an arbitrary function of the success of other tests. And here we have a table.
Yeah, so we are comparing the different operators on the different set of statements. So if you have statements, you can basically do anything you want. If you have verifiable statement, you can't do negation, you can do finite conjunction and countable disjunction. But if you have decidable statement, then you can do the negation, but then conjunction and disjunction must be finite.
Finite, you mean in the in the number of statements it involves, or it's in okay. Yeah. Finite disallowed. Okay. So then I continue. Before we continue, it is interesting and useful to stop and understand the interplay between scientific and mathematical constructs. Okay, so I read the footnote. It took us many confusing years to fully understand where the scientific argument ends and the mathematical argument begins, what makes sense to assume physically and what makes sense to prove rigorously. Part of the confusion is that this line is not objective, but it is based on what is considered precise by a mathematician, which has evolved considerably through the centuries. The rule we follow is, in the mathematical formalism, the only objects that can be left unspecified are the elements of a set. Okay, so it technically, yeah, these
those are the 6 axioms that
axioms of our mathematical formalism for statements. Note that the actual content of these statements, the methodology for which an assignment is deemed possible, and the procedures for experimental verification are not formally defined. The math simply uses symbols to label and identify them. The only assumptions are that statements exist, organized in logical contexts with possible assignments, one of which is the true one, that some of them are verifiable, and that they admit the associated algebra. The mathematical formalism does not know what the symbols actually represent. They may as well be pieces of cardboard painted black or white. The math can only derive consequence given the premise, but it does not know whether the premise makes actual sense. In other words, the way that we are making the framework mathematically precise is not by making everything mathematically precise. It is by omitting the details that are not amenable to a precise specification.
We should stress this for a couple of reasons. First, the part that is not formalized is the most important part. Discovering new science is exactly finding new things to study, i.e., new statements, new connections between new known objects, i.e., new logical relationships, or devising new measurement techniques, i.e., new experimental tests. The content of the statements, their semantic relationships, and the procedure of the experimental tests is the actual science. Everything that follows is, in a sense, the trivial bit, and that is why it can be done generally. Um, which leads to the second reason. Understanding whether statements and verifiable statements actually follow the algebras we defined is crucial. The math just takes it at face value and doesn't prove it. The justifications for our axioms, then, are the most critical part of this work, and they are not mathematical proofs. If we botch them, we'll have a nice, consistent, rich, but meaningless mathematical framework. Lastly, it has to be clear that something gets lost in the formalization. The mathematical framework cannot carry all the physics content. We removed the most important part. Different systems may have the same mathematical description, so the scientific content can never be entirely reconstructed from the math. That is why we always have to carefully bring it along. Yeah. Um,
Yeah, and note that we are is actually doing, because this is the complete opposite of what we currently do in physics, right? Where you just set some math and then you try to find observables and so on. Like, yeah,
yeah.
it's never gonna end.
Okay, I'll just go up to the definition, I suppose. Yeah. Now that we've characterized verifiable statements, we want to understand how to characterize groups of them. Consider the verifiable statements. That animal is a duck, that animal is a swan, that animal is white or black, or is a black swan, or is a white duck, or is a duck or a swan. Since some depend on others, we do not need to actually run all the tests. Once we have tested the first four, we've gathered enough information for the others. We call this set a basis.
Uh, okay, so then there is a footnote. The term basis is used in general to define a set of objects from which, through a series of operations, one can construct a full space. It is the same for a vector space. From a basis, one can construct any other vector through linear combination. What changes is what objects are combined and what operations are used. Okay, so the definition is given a set D of verifiable statements, set B, a subset of D, is a basis if the truth values of B are enough to deduce the truth values of the set. Formally, all elements of D can be generated from B using finite conjunction and countable disjunction. Note that once we have tested the basis, we have tested any other verifiable statement that can be constructed from it. In the example before, once we tested the first four, we have implicitly tested that animal is a black duck. It is also true that impossibilities and certainties don't really need to be tested. We already know that that animal is a duck and a swan is false. The idea then is to group verifiable statements into experimental domains that can be seen as all the experimental information one can gather for a particular subject. These will include the certainty, the impossibility, and any other verifiable statements that can be constructed from a basis. The basis, though, has to be countable so that by running one test at a time, we can hope to eventually reach any element.
Right. Definition 1.35. An experimental domain D represents a set of verifiable statements that can be tested and possibly verified in an indefinite amount of time. Formally, it is a set of statements closed under finite conjunction and countable disjunction that includes precisely the certainty, the impossibility, and a set of verifiable statements that can be generated from a countable basis. Justification. In principle, indefinite is different from infinite. Having infinite time at our disposal literally means we can go on forever, which we cannot do. Having indefinite time means that, well, at some point we have to stop. We have to be prepared to keep going on because we do not know when we will stop. In practice, in both cases we have to make a plan for an infinite amount of time. In the indefinite case, our plan will be cut short. And as we've already argued, we cannot run uncountably many tests in infinite time. Let E, a subset of the set of experiments, be an uncountable set of experimental tests. Let T0 be or T0 be the amount of time that the shortest test will take to run. Each test will run for t0 time. Given that each test will succeed in finite non-zero time, at best t0 is a finite number. We can divide time into slots of t0 time. The slots will be countable. As E is uncountable, we cannot associate each test to a slot, and therefore we cannot test uncountably many tests. We can, however, test countably many tests. Let a basis B be some countable sequence of experiments EI. Then we can proceed as follows. 1, initialize n to 1. 2, for each I from 1 to n, run the test EI for n seconds. And then 3, increment n and go to step 2. This will run all tests for an indefinite amount of time. Now, let D, a subset of S, be the set of statements generated by B using finite conjunction and countable disjunction. Then D is a subset of the set of verifiable statements, well, because we can run that procedure. Furthermore, testing B will eventually verify each true statement in D. Therefore, we are justified to assume that a set D is a subset of verifiable statements that can be tested in an indefinite amount of time must have a countable basis. We are also justified to assume that it contains the certainty and the impossibility, as these two are verifiable statements, and two verifiable statements can always be added to a countable basis and keep it countable. This justifies the definition.
Okay, we can think of an experimental domain as the enumeration of all possible verifiable answers to a scientific question. For example, the domain related to the question, what is that animal, would include it is a mammal, it is a dog, it is an animal with feathers, and so on. If two statements are possible answers to that question, then their conjunction and disjunction will also be possible answers. For example, it is a dog or a cat, or it is a mammal and it lays eggs. While each statement only needs finite time to be verified, we allow indefinite time for the domain because we want to capture those questions that can be answered only approximately. The idea is that given more time, we can always get a better answer. So in principle, we have an infinite sequence of tests to perform and continue indefinitely. The basis not only serves as a way to constrain the size of the experimental domain, but most of the time it will also serve to define the experimental domain itself. We will typically start by characterizing a set of verifiable statements, e.g. a set of characteristics of animals and how to identify them, and then consider the domain of all the verifiable statements that can be constructed from them, e.g. the set of all animals and groups of animals we can identify.
Okay. So that's basically the building block. That experimental domain, we'll use it all over.
Sorry, I had the question. I don't know if it's like if it's here, but so of course we are limited only to this countable number of tests. But let's say, I don't know, we want to test, we want to successfully test, let's say, a value of some constant. So we measure and measure and measure with each test, and we could imagine that, for each decimal value, that's we would have a new experiment. But then we could replace them with just one experiment that does it much better.
Yeah.
So is this any way like allowing us to, how to say, compactify like an infinite uncountable number of tests into like a countable one, or there's something wrong in this
No, so
thinking?
it's exactly what happens. So imagine the real line, right? So you're measuring a value on the real line. And what you do is you can imagine all the possible finite precision measurements. And in fact, you can imagine those that where the range are two rationals. Right, so now you have the set of all the possible intervals with rational numbers. That's going to be countable. And that's a basis. Now, because each real number is the limit of a sequence of rationals, you can always, zone in, and with countably many, you're gonna get the infinite precision of a real,
Mm-hmm.
right? And so you're gonna be able to, from those with the countable disjunction, you can also make intervals that are from real to real, right? So if you imagine that you want the interval from 0 to pi, you take the one from 0 to 3, and then from 0 to 3.1, the 0 from 3.1, you make the disjunction of all that, you make the union of all those sets, you're gonna get all the numbers between 0 and 3 and pi.
Mm-hmm. Mm-hmm.
So these are the
Okay.
type of things that people do in topology, right? And that's exactly what we justify from these axioms.
Mm-hmm. Okay, then my thought was if I take the analogy of, let's say, these real numbers in in the neighborhood of all these rational numbers, uh, and also take, for example, the in the quantum mechanics, these states that are how to say, behaving very badly, but because we have this no dense how to say dense subsets, we can how to say how to say approximate them, arbitrarily closely. So in quantum mechanics, this suggests that okay, maybe we should not throw out all the machinery of Hilbert space, but
Right.
then we should know that some limits are not, I don't know, physical anymore. So is
Yeah.
it also the case here that this kind of justifies that we can use real numbers, but not always a real number is how to say physically relevant?
So it's a one step forward. So the
Mhm.
fact that you have the real numbers here, the real numbers are going to be the possibilities of your space, right? And so it's the thing that you kind of like in the model assumes that they exist, but you're never going to be able to verify them correctly. Like you're never going to be able to say, oh yeah, I measured exactly pi. No, you're not going to be able to do that, right? On the other side, it's instead making limits that go out of the space itself. Right? So if you say, I have a sequence of probability distribution whose average is finite, but then the limit is infinite. Now, saying that you have an infinite expectation value is different than saying, oh, I can converge in the space. It's a little, that's more like saying, I have a function of real numbers, and that's what I have physically, but then I extend it to the complex numbers because I can then do poles and complex analysis, which is simpler, which is something that you're allowed to do, provided that the solution then goes back in the space. So there are two different things. So here we're just saying that the sort of your spaces of interest are going to have some certain properties. The fact that you can explore them in a countable way, and then there are going to be mathematical spaces that are not explorable in a countable way. So the set of let's say discontinuous functions from R to R, for example, that's not something that you can put a second countable topology. That's not something where you're going to have the tests in that way. And so then you say, okay, this is too big and we can't. So Hilbert spaces, at least, so what you can rule out, it's the non-separable Hilbert spaces. So the non-separable Hilbert spaces don't have a countable dense subset, and therefore you're not going to be able to find a countable collection of verifiable statements that allow you to explore the space. So it's more on that.
Thank you.
All right, should we continue?
Yep.
All right, so 1.3, theoretical domains and possibilities. The basis for an experimental domain allows us to create a procedure that will eventually test any verifiable statement. But to fully characterize a domain, we want to find those statements like that animal is a cat or the mass of the photon is exactly 0 electron volts. That one I think falls under that discussion where maybe it's hard to exactly verify that, but that aside, that if true, determine the truth value of all verifiable statements in the domain. The main result of this section is that these statements, which we call possibilities for the domain, are not necessarily verifiable themselves. Ah, okay. So this is exactly what we were talking about.
Yeah.
We will therefore need to introduce theoretical domains, which consists of those statements that can be associated to a test. These tests are constructed from those associated to verifiable statements from an experimental domain. We will also be able to conclude that the set of possibilities for an arbitrary experimental domain has at most the cardinality of the continuum, thus putting a hard constraint on what type of mathematical objects are useful in science. When you say the cardinality of the continuum, do you just mean the smallest uncountable cardinal, or do you mean the cardinality of the real number line? Not that.
Cardinality of the real number line.
Okay.
So 2 to the omega.
Okay, interesting. Yeah. Not that once again, not that it's relevant, just because like in model theory, those can be different. Okay.
Yeah, no, I know. So yeah,
All right.
it's the cardinality of the countable of what's it called of countable sequences of zeros and one, for example.
Okay. All right. Yeah. Suppose that D sub X is the domain of animal species identification. It will contain verifiable statements such as that animal has feathers, that animal has claws, that animal has paws. Some statements are broader and some are narrower. Some statements, like that animal is a mute swan or that animal is a mallard duck, are special because if we verify those, then we are able to know which other statements are true or false. Once we verify those, we're essentially done. These are what we call possibilities of the domain, and enumerating them means characterizing the experimental domain. Yeah, here, I guess.
Okay, unfortunately, not all possibilities are verifiable statements. Consider the statements as one, which is there is extraterrestrial life, and as two, there is no extraterrestrial life. We can create an experiment, test to verify the first, find extraterrestrial life somewhere, but not the second. It would require us to check every place in the universe, which is something we cannot do. So for this question, the experimental domain dx is equals set of S1, what is it? True
Certainty.
and certainty and impossibility.
Yeah.
And is composed of the first statement, okay, and written out. But S2 is conceptually still one of the possibilities. If true, we have a complete answer for the domain. What happens is that while the negation of a verifiable statement is not always a verifiable statement, it is still a statement that can be associated to an experimental test. As such, while we cannot verify the statement, we can still predict the outcome of its test, including non-termination. To be able to find all possibilities, then we have to create the set of statements that can be associated with experimental tests regardless of termination, which will include negations. We call this set the theoretical domain and theoretical statements its elements. So that's a definition. The theoretical domain D bar of an experimental domain D is the set of statements constructed from D to which we can associate a test regardless of termination. Sorry, can we go?
Sorry, like my internet disconnected a minute.
Yeah,
So.
I noticed something. We call theoretical statement a statement that is part of a theoretical domain. More formally, D bar is the set of all statements generated from D using negation, finite conjunction, and countable disjunction. Justification. The theoretical domain is defined to contain all statements that depend on the verifiable statements for which we can associate an experimental test. A statement in the theoretical domain, therefore, must be associated to a procedure that can be constructed in terms of the tests of verifiable statements, regardless of whether the procedure is guaranteed to terminate. First of all, any verifiable statement is a theoretical statement. In fact, let S be a verifiable statement. Then there is a test E associated to S. Therefore, S is a theoretical statement. In the previous justifications, we saw how to construct tests for negation, finite conjunction, and countable disjunction. We can use these to construct tests of theoretical statements from other theoretical statements. Let S be a theoretical statement. Then there is a test E associated to S. Consider negation of S. This can be associated with a test, negating E. Therefore, negation of S is a theoretical statement. Let Si be a finite collection of theoretical statements. Then there is a finite collection of tests EI, each associated to the respective statement. Consider a finite conjunction of SIs. This can be associated with a test, which is a finite conjunction of EIs. Therefore, a conjunction of Si is a theoretical statement. Let Si be a countable collection of theoretical statements. Then there is a countable collection of tests, each associated to the respective statement. Consider countable disjunction of statements. This can be associated with a test, which is a countable disjunction of individual tests. Therefore, countable disjunction is a theoretical statement. Therefore, we are justified to assume the theoretical domain contains the closure of the experimental domain under negation, finite conjunction, and countable disjunction. As shown later, this will automatically include countable conjunction as well. Note that, as before, this cannot be generalized to uncountable operations, as a procedure can be composed only of countably many non-zero time operations. Therefore, we are not justified to close under uncountable operations.
Because of its construction, the theoretical domain will also include all the limits of all the sequence of verifiable statements. Consider the experimental domain for the mass of the photon. It will contain verifiable statements such as S1, the mass of the photon is smaller than 10 to the negative 1 eV, S2, the mass of the photon is smaller than 10 to the negative 2 eV, and then I guess in general, Sn, the mass of the photon is smaller than 10 to the negative n eV. So this continues forever. And it will not contain the statement, the mass of the photon is exactly 0 eV, though as we cannot measure a continuous quantity with infinite precision. Note that S, the statement that the mass of the photon is exactly 0, can be seen as the limit of the sequence of ever-increasing precision, but can also be seen as the conjunction for all those statements. In fact, the mass of the photon is exactly 0 if and only if all of the finite precision measurements will contain 0 in the range. It makes sense then that it is not part of the experimental domain because only finite conjunctions of verifiable statements are verifiable. But we expect S to be a possibility for the mass of the photon. Why should it be in the theoretical domain? So because of the De Morgan properties in 1.19, we can express conjunctions in terms of negation and disjunction. So we have that S equals the conjunction of all the SIs, which is equal to the negation of the disjunction of the negation of all the SIs. Okay. Therefore, by allowing negation, we also allow for countable conjunction, and therefore we include all the limits of the sequences of verifiable statements. Right, so this is I think just stated in proposition 1.37. All theoretical domains are closed under countable conjunction. By proof, any countable conjunction is equivalent to the negation of the disjunction of the negation. And so as the theoretical domain is closed under negation and countable disjunction, it is also closed under countable conjunction. The definition 1.38 is that a theoretical statement is approximately verifiable if it is the limit of some sequence of verifiable statements. Formally, S as in D bar is approximately verifiable if there exists a sequence Si, a countable sequence Si, such that S is the conjunction of all of those statements. So is there a nice way of, I guess the way we're defining the limit of a sequence of statements is just by taking the countable conjunction of it, right?
Yeah.
Okay.
Yeah.
Makes sense.
Okay.
So it's like how you make a sequence, like limits of sets in a way. If you have a sequence of sets that it's a decreasing sequence, right? Then the limit is the conjunction. Is the intersection.
Okay, note that we are closed under countable operations and not arbitrary or uncountable. Therefore, there could be statements that can be constructed from verifiable statements that are not even theoretical statements. One such statement, for example, could be constructed given a set of U of possible mass values for a particle that is uncountable, has an uncountable complement, and where the elements are picked arbitrarily and not according to a simple rule. So the footnote says, mathematically, we are looking for a set of real numbers that is not a Borel set. The statement, the mass of the particle expressed in electron volts is in the set U, can only be tested by checking each value individually. But since the set is uncountable and a procedure can only be made of countably many steps, it will be impossible to construct a test for such a statement. A theoretical statement, then, is one for which we can at least conceive an experimental test. This may not always terminate if the statement is true, or it may not always terminate if the statement is false, but at least we have one. The statements that depend on the experimental domain, but are not part of theoretical domain, do not even hypothetically allow for a procedure, regardless of the fact that it can terminate, and therefore we do not consider them part of our scientific discourse, even theoretically. In general, given a theoretical statement as bar, we would like to characterize what experimental test can be associated to it. Ideally, we want the experimental test for that statement that terminates successfully or unsuccessfully in the most cases. Consider all the verifiable statements that are narrower than S bar. If we take their disjunction, we get the broadest verifiable statement that is still narrower than S bar. We call this the verifiable part of S bar, noted var of S bar. Testing var of S bar means running the test that is guaranteed to terminate successfully in the broadest situations in which S bar is true. In fact, S bar itself is itself verifiable, then var of S bar will be exactly S bar. Conversely, consider all the verifiable statements that are incompatible with S bar. If we take their disjunction, we get the broadest verifiable statement that is still incompatible with S bar. We call this the falsifiable part of S bar, noted fal of S bar. Testing fal of S bar means running the test that is guaranteed to terminate successfully in the broadest situations in which S bar is false. In fact, if S bar is itself falsifiable, then fal of S bar will be exactly negation of S bar. Okay. To each theoretical statement, then we associate the experimental test constructed by returning successfully if the test for the verifiable part succeeds, and returning unsuccessfully if the test for the falsifiable part succeeds. We will not be able to terminate if either of those does not terminate, which will correspond to the statement negation of var of S bar and negation of fal of S bar being true. We call this the undecidable part of S bar, noted und S bar. In light of this, consider the statement, the mass of the photon is rational as expressed in electron volts. It is the disjunction of all possibilities with rational numbers, which is countable, and therefore is a theoretical statement. Since we can only experimentally verify finite precision intervals, each verifiable statement will include infinitely many rational and irrational numbers. Therefore, no verifiable statement is narrower than S, and therefore var of S is equivalent to impossibility. But for the same reason, no verifiable statement is incompatible with S, and therefore fal of S is equivalent to impossibility, which means undecidable part of S bar is equivalent to certainty. This means that the experimental test for S will never terminate either successfully or unsuccessfully. We call this type of statements undecidable, as we will never be able to experimentally test anything about them.
Okay, makes sense. So you're basically taking a statement and say, okay, which part is the part that terminates, which part is the part that does not terminate, and which part terminates successfully and unsuccessfully. So there is a comment from the chat that says, hey guys, I've been thinking about this in Cosenza. You were talking about things that are similar to the question, which came first, iron or the melting point of iron? I will say I'm just passing by. Okay, so right now we're basically looking at just the logic of how sort of things with tests, work. So this basically is of extremely broad applicability, and because it wants to be very general, so it can basically be applied to anything. Okay, let's proceed to the definition 139.
All right. So this definition is basically just what Julia said, but maybe more formal. Definition 1.39, let S bar and D bar be a theoretical statement. We call the verifiable part verif S bar, which is equal to the disjunction of all elements in D, such that they are, I guess, narrower than, yeah, is the broadest verifiable statement that is narrower than S bar. It says it there. We call the falsifiable part fall of S bar, the broadest verifiable statement that is incompatible with S bar. We call the undecidable part und of S bar equal to the negation of the verifiable part of S bar and negation of the falsifiable S bar, or the broadest statement incompatible with both the verifiable and the falsifiable part. So justification, let E sub S bar be the optimal test for S bar and D bar, that is the experimental test constructible from those associated to D that terminates under the most condition. Let var of S bar be the verifiable statement associated with that test. And we must have that, this is a, this is an element of D, since it is constructible from elements of the domain. And I can consider S sub disjunction, which is just given by the disjunction of all S and D, such that S is narrower than S bar. Then we have that S disjunction is narrower than S bar, and therefore the test E associated with it must terminate successfully whenever S bar is true. Since E sub S bar terminates under most conditions, it must terminate successfully whenever E terminates successfully. If it didn't, we could construct the test E sub S bar or E, which would terminate in more cases, and therefore E sub S bar would not be optimal. Therefore, we must have that that var S bar is broader than S disjunction. However, we cannot have that var S bar is broader than more
It's strictly
broader
broader.
or equal to, I guess. Yeah, I didn't realize that
No,
was
it's broader or strictly broader. The same you have that you have subset or a strict subset. So.
Okay, so we cannot have that the var of S bar is strictly broader than S disjunction. Since var of S bar is in D, this would imply that var of S bar is broader than var of S bar, and therefore we must have that var of S bar is equal to the disjunction of all of the statements that are that are narrower than S bar. Along the same lines, let fall of S be the verifiable statement associated with the negation of, or the, I guess, the experimental negation of E sub S bar. Noting that S is narrower than the negation of S bar if and only if S is, I haven't seen that symbol before, I don't think.
Not incompatible.
Not incompatible.
Yeah.
All right, only if and only if S is not incompatible with S bar. Maybe I was gone that week. We find that fall of S bar is equal to the disjunction of all elements of D that are not incompatible with S bar. This justifies the definitions.
Yeah, we made it. Okay, it's one of those things that's the math is sometimes harder than to prove something that is completely obvious. So
Yeah.
more clarificatory question from the chat about the melting point of iron. So basically, to have a verifiable statement, whenever you have a real number, you're gonna have a bracket. So you're gonna say the melting point of iron is between this value and this value. That's verifiable. If you have a statement that it's an infinitely precise value, then that statement is not going to be verifiable because we cannot verify at infinite precision, but it's typically falsifiable because if you can measure that it's outside of that range, then you can verify experimentally that that's not the case, and so it's falsifiable. And so these are all, you would have to go and look at all the other things that we did, but the idea is that you have a context where you have all these statements because you have a theory that defines all these statements, and then within this theory something is verifiable, falsifiable, and all that. Okay, now corollary 140.
Right, corollary 1.40. The verifiable, falsifiable, and undecidable partition the certainty. That is, for every S bar and D bar, we have that certainty is equal to or equivalent to the verifiable part of S bar, or the undecidable part of S bar, or the falsifiable part of S bar. While the verifiable part, undecidable part, well, all of them are pairwise.
Sorry, I read. So with the bar is incompatible. Without the bar is compatible. So the verifiable, these are incompatible, not incompatible. Sorry, I got a double negation here. I got distracted.
Yeah, that's okay. I realized while reading this one that yeah. So right, the certainty is equal to the disjunction of all of these things, and they're all pairwise incompatible.
Yeah.
Since proof, we have that this just comes from we have the undecidable part is equal to the negation of the disjunction of the verifiable and falsifiable parts, just using De Morgan's laws. And
Yeah.
so we have that certainty is equivalent to und or not und just by the law of the excluded middle, which I suppose makes sense to assume in this context, which then is equivalent to the disjunction of und, ver, and fall. And then since the var of S bar is narrower than S bar, and fall of S bar is incompatible with S bar, we have that var is incompatible with fall, since und is equivalent to the negation of var and fall, or the conjunction of the negation of var and fall, which is narrower than the negation of var. It's incompatible with var. And similarly, we have that it's incompatible with the negation of fall of S bar, and therefore und and fall are incompatible. So it's just essentially by definition, we've
Yes.
constructed the undecidable part of S bar to be the thing that is incompatible with the other two, and also is the rest of the stuff.
Yeah. So the since you talked about the law excluded middle, so what it's being clear, right? It's made more and more clear, hopefully, is that we have the law of excluded middle for the standard statement. So when we do a negation, it's an actual negation. But when we go on the experimental verifiability, right? Like you have this sort of undecidable part, which is not like when you're going to do the negation, the verifiable becomes the falsifiable, but it's the and that you don't know how to split. And it's because we have both logics, the one on the statements and the one on the verifiability, that we know where to split the undecidable for the three value logic. Where in principle, if you didn't know how to do that, then you wouldn't have the law of excluded middle. So even though we have the three value logic, we still are able to define a negation because we have it on the two value logic.
That makes sense. Yeah, right. I guess I can finish with this block. But corollary 1.41, a theoretical statement S bar and D bar is verifiable if and only if S bar is equivalent to var of S bar, and is falsifiable if and only if its negation is equivalent to the fall of S bar. It's decidable if and only if und of S bar is equivalent to impossibility. Yeah, proof. Let S bar be a verifiable statement, then S bar itself is the broadest verifiable statement compatible with itself, and therefore S bar is equivalent to var of S bar. Conversely, let S bar be equivalent to var of S bar, then S bar is equivalent to a verifiable statement and is therefore verifiable. Let S bar be a falsifiable statement, then not S bar itself is the broadest verifiable statement incompatible with S bar, and therefore not S bar is equal to fall of S bar. Conversely, let not of S bar be equivalent to fall of S bar, then not S bar is equivalent to a verifiable statement, and S bar is therefore falsifiable. Let S bar be a decidable statement, then und of S bar is equal to not var of S bar and not fall of S bar, which is equivalent to not S bar or not S bar, which is equivalent to not S bar. Wait, no, not S bar and not S bar, which is impossible. Conversely, let und of S bar be impossible, then or be impossibility, then var of S bar and fall of S bar are two incompatible statements whose disjunction is a certainty. This means that var of S bar is equivalent to not fall of S bar. Since not fall of S bar is equivalent to var of S bar, which is narrower than S bar, which is narrower than the negation of fall of S bar, which is equivalent to var of S bar, then S bar is equal to var of S bar, and not S bar is equal to fall of S bar. Therefore, S bar is decidable. Whew. Yeah. Some of these very obvious statements do get very in the weeds. Yeah, so as a corollary for every theoretical statement S bar, the undecidable part und of S bar is a falsifiable statement. Proof, since the undecidable part is equivalent to the negation of var or fall, then it is the negation of a verifiable statement it's the negation of a verifiable statement and therefore falsifiable. Definition 1.43, theoretical statement S bar and D bar is undecidable if the undecidable part of it is equivalent to certainty.
It's a certainty, yeah.
Right, makes sense.
Oh, we are at 10. Let's see. I think, yeah, I think we stop here, right? There is nothing here. Yeah, I would just stop here at this point and see if there are questions, if you guys have questions.
Well, I have a question, but more about, let's say, like long-term strategy of development of this kind of logic,
Yeah.
because now we are talking about, well, first we talked about this Boolean logic, then about all this experimental verifiability, and we already mentioned several times that this should be the foundation of topology, something like that. And then from that, I think if I remember from other videos of yours that you would like to derive to prove that all these numbers like integers, rationals, maybe real numbers are actually like how to say realizable in some scientific verifiable way, and that maybe even you could go into calculus also to build just to make sure that you're using only the mathematical structures that make sense.
Yeah.
So but if that is the long-term like goal, then this sounds a bit weird, because now we are talking about experiments which can be verified in finite time, it cannot be verified, and somehow this should end up being topology and calculus. It sounds it reminds me a bit of this Gödel's theorems, where this logical statements converted to products of prime numbers and then just try to see what factorizes when. So it's completely, how to say, the original meaning is completely replaced by something else. But if that emerges, then this is a really nice idea. It's like we really like by forcing to think about what is experimentally verifiable and scientific, instead of what is like logically consistent, we can how to say, like purify the structures that these some structures that would lead to the correct mathematics, useful mathematics, if I might say that. Does that make sense?
That's exactly what happens. So if you just take mathematical structures and you define those things, you are gonna get things that are too big, in which things are not possible. So you can see already a hint of this when I was saying that there are, let's see, in the example here, right? I'm basically constructing something that has a Borel set and then a non-Borel set, and I say, oh, this thing is not possible, right? In fact, what we're gonna see exactly that the only sets that we're interested in are going to be Borel sets of a cycle-countable T0 topology, which means that we are going to bypass the Banach-Starkey paradox, which is the thing where you can take a ball, divide it into 5 pieces, move it around, and now you have 2 balls of the same size. And you can do those things because you're including non-measurable sets, and in specifically non-Borel sets. And what we're going to say is basically, look, when we define our notion of size, we are only going to be interested in sets that come from experimental verifiability, therefore sets for which we have experimental tests. And by doing that, we're going to be avoiding all those paradoxes that come when you're trying to consider all the subsets of Rn. And it's like that in multiple cases. Right? So the whole thing should be that when you come from the right mathematical definition, the right physical definition, or the mathematical definition that map correctly to the physics, you get math that is extremely well behaved. And so the idea is to carry out this program to the end, which of course I'm still, I have pieces that still need to be done, especially in the ensemble spaces part. In this section, there are lots of other questions. But I do think that it works so well for all the things up to topology and sigma algebras and so on, that I'd be completely shocked if the things didn't go forward. I think it's just go. It's just that with infinite dimensional spaces, there are a lot of like things where my intuition is not working, well, also a lot of intuition of other people is not working, and we still have to find what are the bits that we can rely. And what it seems to me is that, for example, that in physics we are going to rely on multiple things. Like, yes, you're going to have a topology, but you also, for example, when we get more complicated spaces, we are going to have a notion of ensembles, which gives us the linear structure, which gives us an entropy, which is related to the geometry and so on. And so if you only took one structure by itself, just the linear structure, that wouldn't be enough to characterize the space fully in a way that it's nice and works. So I think that once we figure out what are all the axioms that you basically say, okay, this is a well-defined physical problem, then a lot of the math will come out.
Just to continue a bit, might it be that so when it comes to these paradoxes or these accountability issues, I understand that we can have like such two situations, that in one case we might have something that is let's say not experimentally like feasible, but might correspond to closure of sequence of verifiable things. But then we might also have these paradoxes which are living in completely different universe, which are out of touch. Like, for example, with this, like in quantum mechanics, like I understand when it sometimes makes sense, but this Banach-Tarski paradox, it would be difficult to imagine that this could be like limit of something that is allowed in in this approach that we're pursuing now.
Right. Yeah. So there are things like as we said before, there are different degrees. There are things that we kind of know that they don't exist, but we assume that they exist in some kind of a physical, well-defined way, like the real numbers. We're assuming that we can make precision like a better and better and better in precision. We know that it's not true, but in the model we do it and we work. Then there are things where we're taking a limit in the model and we go outside of the model, such as like a delta function, for example, right? A delta function is a distribution that becomes more and more tight, right? That we're going outside of the model, because even theoretically we know we're not going to be able to do that. Like it just doesn't exist. But it's convenient because it's a convenient tool that allows you to do it. So you're going outside of the model, but you're still a limit of what the model allows. And there are things that cannot even be seen as the limit, like, for example, the set of all the possible subsets of R, they are not the limit of the sets that we're going to be interested in. And then it's really completely mathematical thing that is completely outside. And so what this physical mathematical approach allows you to do is to pinpoint where you are in all those things. And so you know where, okay, I'm still in my valid assumptions. I took my assumption, and within the valid assumption, I make a limit, so I'm outside my assumption, but I can still learn something, or I'm completely outside, and I shouldn't expect and nothing to work.
Will you at some points when we start how to say experimenting these limits, how will we have some criterion to decide that the limit is behaving as nicely as all the elements in the sequence? Like, is there some universal approach, or is like we'll have to define it as we see them?
So the topology and the space will be different case by case.
Mm-hmm.
But if you are converging in the space with the topology, then you know that you're doing a correct limit, one that doesn't violate anything. If the limit does not converge in the space, either because the limit is not in the space or because you're not using the topology of the space, then you know that it's, the sequence exists, but the point that you converge to, it's not in the space, so you're in the second case. And if you have a space that does not fit this basic idea that the space have to have a countable basis and all that, then you know that you have something that is completely unphysical.
Thank you.
Okay, so we stop it here, and I'll see you guys next week, and also for bye for the people who followed us and Cam Valid 6373. Thank you for joining us, and I'll see you guys next week. Bye.
See you next week.